Dear students, we are discussing about the IS specifications of materials. Now we come to the next material, that is alloy steels. You know, alloy steels are also iron carbon alloys. Plain carbon steels are also iron carbon alloys. But in alloy steels, you see, they contain higher percentage of manganese or silicon than that is specified for the plain carbon steels, or significant amounts of other alloying elements like nickel, chromium, molybdenum, vanadium, tungsten, etc. There may be other elements also. Okay, you see, one thing you remember, this manganese will be there even in plain carbon steels, but the amount will be less. Okay, and the silicon, because it is dug from the earth in the ore itself, silicon means what? Sand. Okay, that will be there present. So in some part, minute particles of silica will be there. Okay, so though manganese, silicon and other such elements are there in plain carbon steels, the amount is very less. But when you say alloy steels, the percentage of these things will be more, and also there will be other alloying elements. These alloying elements may be like nickel, chromium, molybdenum, vanadium, tungsten. These are the things purposefully when you are making steel you add in the steel plant. In the steel plant, when it is molted, when the iron is in a liquid state, at that time you add chromium, you add nickel, you add molybdenum. Why are we adding it? See, here it is written, the alloying elements are added to improve the mechanical properties. Okay, so actually these all things you must have already studied, but now if you are talking, it is only for revision, so I'll be briefly covering. Ah, okay, chromium, it improves hardness, hardenability, wear resistance, and corrosion resistance. You see, chromium main it is corrosion resistance. You see, if in a steel some 11%, 10.5% to 11% of chromium is there, then that steel becomes stainless steel. That means it will not corrode, it will not rust. So if you want corrosion resistance, you should ensure that in the material 10.5 to 11% and more than that, chromium should be present. And also, apart from the corrosion resistance, which is of the prime importance, chromium also increases the hardness. I told you hardness is necessary for maintaining the blade of the cutting tool. वो जो है ना, हर चीज का जो भी हथियार होता है, औजार होता है, उसका दार कायम रखने के लिए, दार अगर नहीं है तो काटेगा नहीं, दार कायम रहना है तो हार्डनेस होना जरूरी है. ये हार्डनेस बढ़ाने में क्रोमियम का भी एक मात्रा है. क्रोमियम ऑल्सो प्लेस अ रोल. एंड देन द हार्डनेबिलिटी improved by chromium. वेयर रेजिस्टेंस मतलब घिस जाने का जो है, घिस जाना कम करता है, so wear resistance. It also improves elevated temperature behavior of steel. You see, mostly all our properties that we are seeing, stress strain diagram and all these things that we are seeing, they are the behavior of those materials at the room temperature. Room temperature means around 27 degrees centigrade. But if it is, if a material is working somewhere in high temperature places, like in in boilers, or in turbines, or in IC engines and such places where high temperatures of 500 degrees, 600 degrees, 1000 degree and more degrees centigrade is there, then some of those materials will not exhibit the same behavior. But if you want to have the same maintain the behavior of those materials at those elevated temperatures or high temperatures, this chromium helps. So that's why chromium is added. Then nickel improves its toughness, ductility, strength. Uh, but actually, some people think nickel is also responsible for corrosion resistance. Yeah, in stainless steels, nickel also is there. When nickel and chromium both are there, then they are called austenitic stainless steels. But nickel is not alone, is alone cannot do the corrosion resistance. For corrosion resistance, chromium should be there. Okay, nickel also helps. It improves toughness, also ductility, strength, and it reduces distortion during heat treatment. So when you are heat treating, this metal bar should not get twisted like this. Okay, so this case harden of steels, of nickel steels, results in better core. Core means the heart, inside part is called core. Better core than obtained with plain carbon steels. So nickel in these ways it helps. And manganese is added to all steels as a deoxidizing and a desulfurizing agent. Okay, but this sulfur should not be more than 1%. The steel is, yeah, okay. If the sulfur content is low and the manganese content is over 1%, the steel is classified as manganese steel. It improves the strength of the steels in both hot rolled and heat treated condition. Then silicon. Silicon, I said, as I told you, it is coming because of the sand that is present in the ore, iron ore. Okay, but sometimes it is added also because it acts as a deoxidizing agent. Deoxidizing means, it is fighting against corrosion. That is deoxidizing. See, oxidation is taking place means what? Iron is being converted into iron oxide, and it becomes rust and falls off. So if you are deoxidizing means rusting will be reduced. When added to as an alloying element, it improves elastic limit and resilience. These properties it improves. Then molybdenum. Molybdenum, it improves hardenability, hardness, toughness, high temperature strength, and creep resistance. Vanadium improves hardenability, toughness, and fatigue strength. And then tungsten, it improves hardness, toughness. Okay, it maintains hardness even at red heat. Red heat means elevated temperature. When it's very hot also, it maintains its hardness, and hence it is widely used in tool steels. See, this material tungsten is present in tools, in making steels that are made, that are used for making tools. Tools, what is necessary is that sharpness of the blade edge should be maintained. Its effects is similar to that of molybdenum, except that it must be added in greater quantities. Tungsten should be added in greater quantities, and this molybdenum also is doing the same thing. Okay, okay, now coming to the how designation is done. Now designation is a, now here there is an example. First example, 20Cr18Ni2. Okay, before this I want to show you some other table. Yes, you see here in the table there is a multiplying factor for alloying elements in steel. See, if it is chromium or cobalt, nickel, silicon, or tungsten, the multiplying factor is 4. You have to remember this table. Then this aluminum, I think this is beryllium, vanadium, this lead, and copper, niobium, titanium, zirconium, and molybdenum. For this, multiplying factor is 100. And for phosphor, sulfur, and nitrogen, the multiplying factor is, for this it is 10, for this it is 100. Okay, so here is an example. You see, 25Cr4MO2. See this, it will be given like this, and you have to identify which material it is. When you see like this, you have to say this is an alloy steel. This is an alloy steel. Okay, and it has an this first number. This is the carbon percentage. Okay, carbon percentage, that as before you have to divide this by 100. So what will be the carbon percentage? Carbon percentage will be um, what will be the carbon percentage? Carbon percentage is 0.25%. It is written here. And then you see, letter C need not be written. Letter C is missing, but still this number is for carbon. Then Cr. Cr is standing for chromium. And this is 4. You see, in this table you should come and see. Cr should be divided by what factor? Multiplying factor is 4. So this 4 divided by 4 comes 1. That means 1% chromium. Then next is MO. MO is molybdenum. Molybdenum is here. Its multiplying factor is 10. So this divided by 10. 2 divided by 10 comes to 0.2%. So then this comes to you see 0.2% molybdenum. Okay. Similarly, another example here, 40 Ni8Cr 8V2. What is the material? When you should be able to say this is an alloy steel containing, this is what, 40 is what, carbon percentage divided by 100. That means 0.4% carbon. Then what is this this Ni8? Ni8 is, you see, Ni you should come to the table and see. Ni is multiplying factor is 4. So divide this 8 by 4, that you get 2. That means what? Nickel is 2%. You see, it is written here 2% nickel. Are you seeing it? And then again Cr8. Cr also in this table Cr also has multiplying factor 4. So this also should be divided by 4. So 8 divided by 4 is 2. So what we are seeing here is this is 2% chromium. You see? And then V is for vanadium. See the table? This is multiplying factor 10. So 2 by 10 is 0.2. So 0.2% vanadium. So how you should say? When you should say this is an alloy steel containing 0.4% of carbon, 2% of nickel, 2% of chromium, and 0.2% of vanadium. That's how you should be able to say. Okay. Okay, another example, 15 Cr3. 15, what is this? This is carbon percentage. How much is carbon percentage? Divided by 100. It becomes 0.15% carbon. This is an alloy steel having 0.15% of carbon, and Cr is 3. Cr is 3 means what? You see, chromium, for chromium you have to divide by 4. Is it not? So if you are dividing by 4, whatever comes, so much percentage of chromium. That you should be able to say like that. Okay. Some other example. Okay, coming to this example, the following example illustrates the designation. 28 Cr 18 Ni2. No. Actually, here it is not given correctly in this book. I will show you how this should be given. Yeah, come and see this example. Is a X15 Cr25 Ni12. See this letter X. You see this letter X shows that this is the high alloy steel. You see, alloy steels can be two types: low alloy steel and high alloy steel. First, till now what we have seen without the letter X is low alloy steel. X is not there means low alloy steel, but X is there means high alloy steel. Okay, that table that I have shown you with the multiplying factors, it is for low alloy steel, not for high alloy steel. For high alloy steel, if we are giving like this letter X indicates it is the high alloy steel, and this 15, this is the carbon percentage. Carbon is should be divided by 100, so 0.15% carbon, and this chromium 25, when it is high alloy steel, this should be given as it is. That is, multiplying factor is 1 in that case. That means 25 percentage of chromium, and nickel also 12, fully you have to give, so 12% of nickel. When X15 Cr25 Ni12 is there, what you should say, this is a high alloy steel which has 0.15% of carbon, 25% of chromium, and 12% of nickel. That's how you should mention. Another example here, X20Cr18 Ni2. You see, the moment you see X, you know that this is high alloy steel. And high alloy steel having 0.2 percentage of carbon, 18% of chromium, and 2% of nickel. Here another example, X10Cr18Ni9. That means it is an high alloy steel having 0.1% carbon, 18% chromium, and 9% nickel. Here you see another question, identify the material and its composition. This, like this. You see, the moment you see X, you should say it is a high alloy steel. This is 0.10% of carbon, 18% chromium, 9% nickel, and 4% molybdenum, 2% silicon. And again this one, it is an high alloy steel. You see, when you come across X, it is high alloy steel. And see, this 7 should not have been typed. It is only 72. It should be. So 0. You see, here it is given average carbon percentage, 0.72% of carbon. This cannot be more than this cannot be okay. This cannot be 7%. Carbon won't be there in any steel. Okay, the steel can have maximum 2%. That means it can be up to 200 only. It cannot be 700. So this is only 72. So 0.72 percentage of carbon, and W is tungsten. So 18% tungsten, 4% chromium, and 1% vanadium. Okay, coming to the next material. This is free cutting steel. How free cutting steel is given? It is designated by 100 times the average percentage of carbon. Then letter C will come. Letter C was coming even in low carbon, plain carbon steels. But after C, it is followed by either S. S is for sulfur, or lead, Pb. These two, if it is following, then it is a free cutting steel. You should be able to see. You see, if it is only this much, 25C12, then it will become plain carbon steel. But if when S14 also is added, then it becomes free cutting steel. So this is free cutting steel having 0.25 percentage of carbon, and uh, and this one should be divided by 100. So 0.12% of oh, wait. This material, this is manganese. This is manganese. No, earlier we have seen when this much part is not there, we knew that this was carbon percentage, this was manganese percent. So this is 0. This is a free cutting steel having 0.24 percentage of carbon, and this should be divided by 10, because manganese should be divided by 10 in plain carbon steel. So 1.2 percentage of manganese, and this should be divided. Sulfur, no, very less. It is always less than 1 only. So this should always be divided by 100. So 0.14% of sulfur. So how do you say this? This is free cutting steel having 0.25% of carbon, 1.2% of manganese, and 0.14% of sulfur. That's how you have to say this. Okay, next material. This is cast steel. See, cast steel is different, cast iron is different. See, cast steel is used for casting intricate shapes. Intricate means खिचकट चीजें, मतलब बहुत ही पतले पतले सेक्शंस, और वो मटेरियल जो है ना बहुत नैरो पैसेजेस से जाना चाहिए. मतलब सिंपल शेप नहीं है, कॉम्प्लिकेटेड. इंट्रिकेट बोले तो एक तरह का कॉम्प्लिकेटेड शेप्स होते हैं. सो cast steel is used for intricate shapes. The advantages of cast steel components over the cast iron components are as follows. Cast steel are lighter and stronger. कास्ट आयरन हेवी बनता है, ये लाइट बनता है, और दे हैव गुड डक्टिलिटी एंड गुड टफनेस एंड हाई एंड्योरेंस स्ट्रेंथ. दे कैन विथस्टैंड फटीग लोडिंग एज वेल एज इम्पैक्ट लोडिंग. जैसे फटीग लोडिंग के लिए कास्ट आयरन यूज नहीं करते हैं, तो कास्ट स्टील थोड़ा यूज कर सकते हैं. और इम्पैक्ट लोडिंग बोले तो जहां पर जैसा इम्पैक्ट लोड आता है, जैसा हथौड़े का मार जैसा आता है. Okay, then they have good weldability. Cast iron is cannot be welded, whereas cast steel can be welded. So cast iron, no, that material, though it is it is a metal, it's an iron alloy, it cannot be welded, whereas this cast steel can be welded. Cast steel components are used for highly stressed casting, gear, हेवी ड्यूटी मशीन रेट्स. हेवी ड्यूटीज में जहां पर गेयर्स वगैरह इस्तेमाल कर सकते हैं, ये कास्ट स्टील यूज करते हैं. सो हाउ इट इज डिजिग्नेटेड? See, designated like this: CS. CS means cast steel, and then some value. XXX means some value. It is followed by 3 or 4 digit numbers indicating the ultimate tensile strength. Okay. For example, we'll see here. Example, CS 840. CS 840 means, you see, this is a cast steel. This material is a cast steel, which has 840 Newton per millimeter square as ultimate strength. That's how you should say. Now here, CS 640. CS 640 is cast steel with 640 Newton per mm square ultimate tensile strength. Okay, this much you should be able to say. Okay. Okay, here I have a material 55C4. What is it? 55C4, only C in the middle and either side two values are there, means this is becomes a plain carbon steel. So this is a plain carbon steel having this divided by 100, that is 0.55. 0.55% of carbon, and this divided by 10, that is 0.4% of manganese. Manganese means Mn, not MC. Okay. Like this, what is this material? This is a plain carbon steel having 0.4% carbon and 0.8% manganese. Okay. What is this material? 25C12S14. You see, had it been up to only this much, then it would have been plain carbon steel. But because this is attached, then this becomes free cutting steel. So this is a free cutting steel which is having 0.25% of carbon, 1.25% manganese, and 0.14% of sulfur. Okay. Another example here. You see, here what all materials can be there for the free cutting steel? This free cutting steel can have sulfur, then Se means, I think it is selenium or something, and then Te, I don't know, maybe it is beryllium, and lead. Okay, any of these four things can come here. Okay, example, see here, 20C12Pb15. If had it been only this much, then it would have been plain carbon steel. But because this is attached, it becomes free cutting steel. So it is a free cutting steel having 0.2% of carbon, 1.2% of manganese, and 0.15% of lead. Okay, that's how you have to specify this. Initially, we have seen about the cast irons. Cast irons we have seen only gray cast iron and spheroidal cast iron. And you see, there is, if it is malleable cast iron, malleable cast iron can have white heart. So if it is a white heart cast iron, the letter we'll be using is WM. And if it is a pearlitic malleable cast iron, it will be PM. So if you have FG150, then it means gray cast iron with 150 Newton per mm square as the ultimate tensile strength. If it is SG150, then spheroidal graphite cast iron with 150 Newton per mm square. But here no, the percentage of ductility also will be there. Whereas WM150, that means it white hard malleable cast iron with 150 Newton per mm square as the ultimate tensile strength. And if it is PM, means pearlitic malleable cast iron with 150 Newton per mm square as the ultimate tensile strength. And you can see here the letter Fe was standing for steel. I told you yesterday. And E is standing for yield strength, and K, if it comes, then it is for killed steel. Killed steel also is one type of steel. You can see, yeah, like this. See, if it is Fe 400K, if by looking at K, you should be able to say this is a killed steel with minimum tensile strength of 400 Newton per mm square. Okay, if it is Fe 350, it is a plain carbon steel with 350 Newton per mm square. And Fe means it is a plain carbon steel with a yield point strength of 380 Newton per mm square. Yeah, here let us see how tool steels are designated. You see, here it is given like 10T4. You see, this is tool steel containing this is divided by 100, that is 0.1% of carbon, and this letter T is for tool steel and 4 is manganese. Had it been C in here, it is plain carbon steel. If it is T, it is a tool steel. That's how it is. If you see here, T70 is there. T70 is tool steel having 0.7% carbon. Fe470W, this is a steel, plain carbon steel with 750 Newton per mm square ultimate tensile strength, and W here stands for it has good weldability. And if you have like this is a this is an alloy steel which has 0.45. No. This is not a license. Plain carbon. No. This is yes, yeah. This is free cutting steel. Free cutting steel which has 0.45% of carbon, 0.1% of manganese, and 0.18% of sulfur. And if you have like this, X and T also. X now we said high alloy steel, but T is high alloy tool steel, which has 0.6% of carbon and 12% of vanadium, 4% of chromium, 12% of tungsten, 4% of chromium, and 1% of vanadium. Okay, so these are all the things normally which are asked. So with this, we come to the conclusion of the designation of the materials according to Indian standards.